Okay, in the next few series of videos, we're going to talk about discontinuities. Makes sense after just talking about continuity. And essentially, a discontinuity is any point where at least one of the three continuity conditions fail. If you don't understand what I'm talking about with these three conditions of continuity, go back to my previous video. I explained that in detail. And today's discontinuity that we're going to deal with is called removable discontinuity, and it's one of the most heavily tested ideas in unit 1 in AP calculus. So, what is a removable discontinuity? It's called that because if you simply redefined the function at that one point, the break would disappear or quote unquote be removed. But we also need to understand the formal definition and especially the notations that define removable discontinuities for the sake of your open response section of your exam. So, a function f has a removable discontinuity as at x equals a if the limit as x approaches a exists, but f of a is undefined. It's not defined at point A. Or another way to say it is f of a is not equal to the limit as x approaches a of f of x. I know this is very theoretical. Math is not much about theory, but actually understanding and being able to calculate. But for the sake of the open response, knowing these formulas is really important because you can literally just get points off of writing down a formula even if you don't get the correct answer. But to make more sense of this, let's work through an example together. So, you have to determine whether this function is continuous at x equal to, and if not, you have to identify and classify the type of discontinuity and be able to justify your answer. So, first, let's check the three conditions of continuity. I'm going to just write them up here in a box for people who might have forgotten. For a function to be continuous, these three conditions must hold. F of a has to be defined. The limit as x approaches a of f of x has to exist. And these two have to be equal. So the limit as x approaches a of f of x has to be equal to f of a. Okay, so let's check with this. Let's check the first condition. Is f of 2 defined? I'm gonna just separate this so we have a lot of space. To check this, I'm going to do direct substitution. So f of 2 would be 2 squared minus 4 over 2 minus 2, 0 over 0. 0 over 0 is undefined, so condition 1 immediately fails. F of 2 does not exist. And normally that would worry you, but let's check condition 2. Does the limit still exist? So because condition 1 has already failed, there's no way this function is continuous. So we already know that this function is discontinuous. But let's check if the limit of this function exists. I'm going to try use a different color. Since direct substitution gave us 0 over 0, that's your signal to factor to figure out the limit. I'm going to go ahead and factor it. If you factor your numerator, you'd have x minus 2, x plus 2 over x minus 2. X minus 2 factors cancel. And this is valid specifically because in a limit, x is approaching 2 and never equal to 2. It's about the journey, it's not about the destination. Whenever dividing by 0, we're getting infinitely close to it. So if we cancel out the x minus 2's, we have f of x is x plus 2. But we also know that it's undefined when x is 2. So x cannot be equal to 2. And because this one is fundamentally this function, we can use it to find the limit. And I think I have a graph of what that looks like a little bit. This is what that graph looks like. So you have the same graph as x equal 2, but at 2, it's undefined. But we can use these to find the limit. We care about how it's behaving as we're approaching 2, not the behavior at 2. So in order to find the limit here, we can go ahead and do direct substitution. So we'd have the limit as x approaches 2 of f of x. If we directly substitute, we'd have 2 plus 2, which will be 4. So the limit exists and it equals 4. And that satisfies the definition of a removable discontinuity, because exactly 2 of those conditions that we're talking about, they hold in this case, where if we redefined the function and had f of 2 is 4, then this hole would be covered and we'd no longer have the discontinuity. But it's a discontinuity because that is not the case. So this is a removable discontinuity. And then an AP exam tip. So whenever direct substitution gives you 0 over 0, this is your signal to factor and cancel. This is the single most common limit technique tested on the AP exam multiple choice section. And then a common mistake that students usually make: don't conclude the limit doesn't exist just because the function is undefined at that point. Those are 2 separate conditions in the definition. So always simplify and check the limit before deciding. I hope that makes sense. See you in the next video.